So in this video, we're going to talk about the formal criterion for conservative vector fields. So we'll go in both directions. We'll start with if a vector field is conservative, what has to be true? And then the harder question to answer is going to be what conditions do we need before we know that a vector field is conservative? Okay, so let's start with the first one. The vector field is PQ is conservative on region D. Then we figured out basically from the previous video that partial derivative of p with respect to y has to be equal to partial derivative of q with respect to x, and that has to be true on all of D. And that's all we need to know. Okay, so that was pretty straightforward. Going the other way is a lot harder. What conditions do we need? Well, we need some things to be true of P and of Q, and we need some things to be true of D. And the stuff with D is harder to define. So let's see, we'll put 3 conditions. Okay, so the easy thing is we actually do need Py equals Qx on D, on all of D, for sure. The P and Q things are easy as well. So P and Q have to be differentiable, and the derivatives have to be continuous. So they have continuous first order derivatives throughout D, so on D. This is not quite as strong as the word smooth. Remember from the previous video, smooth meant infinitely many derivatives. You only need to have one derivative. That derivative needs to be continuous. Okay, and then so F is defined on D, and then we need some conditions about D. Okay, what conditions do we need? Okay, we're doing calculus. Remember from first variable calculus, you had open and closed intervals. Let's say from 0 to 2. You could have the open interval from 0 to 2, which is all the numbers from 0 to 2, not including 0 and 2. And then the closed interval from 0 to 2, all the numbers from 0 to 2, including 0 and 2. Which one of these is better for calculus? For integration, it doesn't make a difference. For derivatives, the open one is a lot better. This one is hard to define derivatives on. You've done it in like very early first variable calculus. We had like one-sided derivatives, so you could define the derivative in the whole interval and then one-sided derivatives at 0 and 2. That's not great for general properties about derivatives, because then you need to treat those points as special cases. So this guy is way better. Okay, let's try to extend that to 2 dimensions. So maybe instead of an interval, I can make a ball, like a unit circle, and the stuff inside the unit circle, and just like with the intervals, I'm not going to include the boundary. So there's an open ball. I can make an open ball anywhere. Pick a center, pick a radius. I can make more interesting open sets, or open regions. There's an open region. And I can maybe like glue a couple together. So that's also an open region. Oh, but if I start allowing gluing together, things could start getting weird, because I might be able to glue together like not just 3, 4, 5 things, but I don't know, am I allowed to glue together infinitely many things? Math people start asking really weird questions. So I need a more formal definition for an open set or an open region so I can check it more easily without seeing what the actual definition, what things are being glued together here, and if those things are open, and like what if they intersect? Does that matter? Is that okay? I'm not sure. So we're going to go to the formal definition, and it just says if D is open, and then P is any point in D, then I can draw an open ball. I'm not going to specify the radius. I can just draw some open ball around P that is entirely contained in D. Okay, so open balls are pretty well defined. It's just the weirder open sets that they get weird. Okay, so what does that mean? That means if I pick a point inside my set D, I can draw an open ball, and certainly I can do that there. I have to be able to do this for every point. So like points really close to the boundary, let's say they're distance little r away from the boundary, I just draw a ball of radius little r over 2. That's okay. So these balls will get really, really small close to the boundary. But check this out. The fact that the boundary isn't contained saves us, because I can always pick a small enough ball. If I took a closed ball, then I can get close to the boundary, and that's still okay. I can pick all the same balls, except now I have points on the boundary that are in the region, and no matter how small any ball that I draw around that point is gonna, there's gonna be pieces of that ball that are outside my closed ball. So that is not open. And in fact, if I include any one point on the boundary, that ruins it. That's now not an open ball. That's not open or closed. That's nothing. So if you go to higher dimensions, or actually we can do this with one dimension as well, but if you go a little bit more complicated than intervals, you can have things that are not open or closed. Okay, so now I can make as complicated a set as I want, and I just check all the points inside. That sounds kind of silly. There's infinitely many points inside, but people who study analysis are okay with this, and this definition actually works pretty well. Okay, so that's what open means, and then we've got to define one more thing, simply connected. So first let's start with connected. Connected means exactly what you think it means. So basically this thing is open but not connected. So what would be the formal definition of that? Well, if set is connected is if I take any 2 points inside, I should be able to draw a curve from one to the other one and stay completely inside the set. Here I can't, so okay, I'm not going to write down that formal definition because that was pretty intuitive. But what about simply connected? This is another concept. So what does simply connected mean? Simply connected means if I draw a circle, inside D, I can shrink the circle to a point while staying completely inside D. Okay, let's see, is that the same or different than connected? Well, if I just have some region like this, okay, I draw a circle, and I start shrinking it to a point, and yeah, I can do it. I can stay completely inside D. Okay, so that guy's simply connected. In fact, this set, if I don't include the boundary, is simply connected, which certainly makes it connected. If we're simply connected, we're connected, and we're also open. That's actually a little bit hard to show that if something's simply connected, then it's connected. Maybe that'll be a future quiz question. I'm not sure. Okay, I can make things that are like this thing is, there's a closed square, so everything inside. That's simply connected, and not open. Okay, so so far it seems like simply connected and connected might be the same thing. So let me draw you a set that is connected but not simply connected. And all we have to do is we have to take an annulus, a ring here. Okay, so this is connected. if I pick any 2 points, doesn't matter, they can be all the way across from each other, I can draw a curve that stays inside. And if I draw a circle over here, then I can shrink certainly that circle to a point while staying completely inside the region. But what if I draw this big circle here? There's no way I can start shrinking the circle. But any way I try to do it, I can't find my way around the hole in the center. Okay, so this is not simply connected. It is connected. And the way I've drawn it, I've included the borders, so it is not open. Okay, what is the issue with this, with vector fields? So let's say I'm trying to make a conservative vector field. I'm trying to make, well, basically, I'm gonna make a nice vector field and show that it is not conservative. It is not the gradient of some function. Remember, gradient is just the direction something grows in. So I'm going to make this vector field. It's just going to be constant arrows going around the circle. And so if things grow in that direction, then let's say my value, so I want f to be del of little f, right? So let's pick a value of little f here. Like, let's say it's 5. It doesn't really matter. We'll see later, it doesn't really matter. Then if I just follow this circle around, then, and I'm following the arrows, so my f value should be getting bigger. By how much, I don't know. So like maybe I'm at 7 here and at 9 here, and I go around, and you know, maybe I've made it to like 25 here. I keep getting bigger, but I'm going to run into a problem because I'm supposed to get bigger and bigger, but I'm going to run back into 5. So there's a vector field in a not simply connected region that seems to be nice otherwise, but it's not the gradient of some little f, because I tried to make a little f at that point, x comma y, and I followed the vector field along and I ran into trouble. Okay, so I can finally fill in where am I? F is defined on some sort of D. Here it is. It's an open and, need more space, simply connected D. Okay, so I need, so the top part was the necessary condition. Here's the sufficient condition. If 1, 2, and 3 are all true, 1, 2, and 3, then imply that my vector field F is conservative. So like this guy was the real math one that we had to check. We had to make sure that worked out with the components of F, big F. These other things are technicalities that might make weird stuff happen, but it is good to know so we can avoid those. And that way, if we check this one, we're not surprised. For some reason, it's not conservative. Oh, it's because it wasn't simply connected, or because the first order derivatives weren't continuous, so something weird happened there. All right, so now we have, that's the formal conservative vector field criterion.